to the South Wales Institute of Engineers Educational Trust, which is a modest charity based here in Cardiff, and but it has a very big history because the South Wales Institute of Engineers represents a very significant 19th century investment in the professionalisation of engineering. It was founded in September in 1857 in a pub in Merthyr. And of course Merthyr is synonymous with iron and steel. And the president was William Menelaus. About William Menelaus, well, he was a Grand Victorian, and he joined Dowlais in 1851 and had experimented with Bessemer, Henry Bessemer, and did pioneering work in addition to his activities of making money at Dowlais. He also, of course, gave his name to all sorts of other things. For example, it was his collection of art and paintings which was given to Cardiff and is the basis of the National Museum of Wales art collection. And indeed, if you go to the museum, you will see a lovely bust of William Menelaus on one of the half staircases as you rise to the top. So I think that's the first phase of introductions. And of course, the next thing is to remind ourselves that this is the 62nd William Menelaus Lecture. And could there be someone more appropriate to give this lecture, given Menelaus's lifelong work in iron and steel at a time when this thing was really changing the face of the world, than our speaker this evening. But Sir Harry, of course, has a very interesting career that, of course, has been available on Radio 4's The Life Scientific and various things, and has had a very, I think, inspiring. Let's have a great time with your lecture, Sir Harry.
Thank you. Thank you very, very much. Thank you. I'm delighted to see you all in the audience and to talk about steels at a location so rich in metallurgical history. Naturally, I'm more than grateful for the invitation from the South Wales Institute for Engineering and Materials Education, and deeply honoured to present the 62nd William Menelaus Lecture. Now, what do I mean about the terms good, bad and ugly in the context of steels and humanity in general? The good part is obvious. When I was a child, I witnessed starvation. In the absence of conflict, there is no starvation. We are able to feed 8.5 billion people thanks to the steel-based mechanization of farming. Now, ugliness is, you will agree, a subjective term. This is a steel sculpture that I photographed near Lincoln, covered in rust and not particularly endearing. And steel is heavy per unit volume, and this makes many less discerning people put it right down the list in terms of specific strength. You must have heard the often repeated and nonsensical story that graphene is 200 times stronger than steel. This lecture is in memory of William Menelaus, a pioneer if ever there was one. I was intrigued by his surname, which has its origins in Greek mythology. Menelaus was the king of Sparta who married Helen, the daughter of Zeus, allegedly the most beautiful woman in the world. At some stage, she either eloped or was abducted, leading to the 10-year Trojan War, but ultimately reunited with Menelaus. So somehow or other, the name made it into Scotland, where William was born, and he then moved to Wales. But before I go into his time in Wales, there was another Menelaus of Alexandria who developed the geometry of triangles on spherical surfaces. So if I wanted to measure the shortest distance between Stockton and Darlington, I would connect them with a straight line. But on the sphere, a straight line corresponds to a great circle, that is, a circle with the diameter of the sphere. This great circle is familiar to all in material science who study crystallography, and you will recall that Bragg was the first lecturer in this William Menelaus Lecture series. William soon became the general manager of the Dowling Iron Works, which implemented the first license to the Bessemer process. Now, at its height, Dowling had 18 blast furnaces producing 88,400 tons of steel per annum. It also provided the rails that connected Stockton and Darlington, the first in the world to carry passengers with the train propelled by steam-powered locomotives. Now, of course, a rail does not have a symmetrical section, so the dissipation of heat from the hot rolling stage is not uniform as the rail cools. Therefore, they bend due to non-uniform thermal contraction as they lie on the run-off table during the cooling stage. Now, the tedious process which was used for straightening them was to press them in a stepwise manner along the length of the rail. So, in 1858, Menelaus patented a rail straightening machine so that rails could be made in a continuous process which involves small deformation while the rail is cold. This kind of technology is now routine in all rail production facilities in the world. Now, most of the current population of the UK will not be aware of the fact that we have the largest number of kilometers of rails installed per unit area in the whole of the world. It really is an asset to our quality of life, one that would not be possible without steel. It is a no-brainer that we should travel by rail and not by car, whether the car is electric or fossil fuel powered. So, just to give you an example, my journey from Cambridge to Cardiff cost just 17 pence per mile. If I calculate the cost of running a car, excluding fuel, then it comes to £2,610 per annum, and that is excluding fuel. The rail and car comparison highlights a recurring theme in my lecture today, that we can reduce CO2 emissions by making the optimum use of steel. Now, rails suffer from two main issues. The first being wear, so you need a certain amount of hardness relative to the hardness of the wheel and the load. The second is more pernicious, rolling contact fatigue, and this is due to a combination of torsion and compression under the rail surface during the passage of a wheel over the surface. And that eventually accumulates to propagate fatigue cracks, which lead to spalling and possibly even greater disasters. Now, most rails have a microstructure which is an intimate mixture of soft ferrite and hard cementite, which is good for wear resistance, but the rolling contact fatigue performance could be better. We invented a completely different rail microstructure containing no carbides at all, just magnetic ferrite and retained austenite, quite a tough combination. And this has a hardness which is no problem and is excellent in rolling contact fatigue resistance. You can see here the relative damage experienced by the perlitic rail when compared with the carbide-free magnetic rail following 90 million gross tons of traffic on a curve. And the picture that you see on the right is the carbide-free magnetic rail installed in the Channel Tunnel, which in 2019 completed 1 billion gross tons of traffic with no grinding necessary. And about a year ago, the French authorities ruled that complicated points, crossings, should be mandated to be made out of the carbide-free magnetic rail. Now, because such a rail would last longer, the cost of or the amount of steel that we produce can be reduced in principle. Okay. Now here is another example of how we can reduce the amount of steel while achieving the same purpose. So I'm going to explain how to get a 25% reduction of steel used in a particular construction of a building. So the same function served by the building, but we use 25% less by substituting ordinary construction steel with microalloyed steel. Now, microalloyed steel was invented in Britain and is stronger than the usual building steels, and therefore it can be used in lesser quantities, although it is more expensive. So here is an actual building which has been put up using microalloyed steel beams, and the consequence of this is that you use something like 22% less steel with 130,000 kilograms of carbon dioxide saved. And although the microalloy steel is more expensive, you use less of it, and therefore the total cost actually goes down. And now you can make even taller buildings using microalloyed beams because they have now become available. And that is, the mass it has per unit volume. It's about 7.8 grams per cubic centimeter is the density of steel. And if you go down to the center of the earth, it's almost twice that, okay, because there's a huge amount of pressure at the center of the earth, and there's about 10 to the power 23 kilograms of solid steel at the center of the earth. Okay, so should we worry that we can't use it for making aeroplanes and so forth? Of course, the vast majority of applications are terrestrial and stationary. So you don't need to worry about those applications. And let me show you something that might amaze you. And although the people who designed this are no longer in my favor, I'm going to show you anyway. Now, should we consider density as a bad characteristic of steel? Bear in mind that most engineering objects are terrestrial and are stationary. But we should not think of strength and density in isolation. For objects that are not stationary, it is the specific strength, that is, the strength divided by density, that matters. Now, these images show the largest rocket ever built, and which has flown quite a few missions already. It is made completely of steel. Both the spaceship and the booster are made of stainless steel, which is in its austenitic condition, but is cold rolled so that the strength is in excess of 2 gigapascals. And the specific strength compares or even beats that of aluminium lithium alloys, which are normally used for rockets of a smaller size. And the steel is only 3 millimeters in thickness, and yet the rocket doesn't collapse under its own weight when it is not pressurized. In the old days, when people attempted to do this using stainless steel, the rockets had to be pressurized in order for them to survive vertically. And this is incredibly easy to fabricate. So here, for example, is off-the-shelf robotics used to make laser welds to construct the rocket essentially like a water tank. So density of steel does not matter. It has been used to create the most powerful rocket in the world. And I'll give you another example in aero engines. So in aero engines, more than 10% of the material in there is steels. And one of the most important components is the shaft of a large civil aircraft engine. And that shaft is made usually from two different steels. One that can be very tough and doesn't experience too high a temperature, and the other end which is a creep resistant chrome moly type steel. And the two then have to be welded together using friction welding and then machining off to create a smooth surface. Now this particular movie isn't about the welding together of two different alloys for shafts, but it's there for illustration purposes. So we wanted, along with Rolls-Royce, to create a shaft material that will serve both the hot and the cold ends of the engine. And remember that steel is actually less dense than nickel alloys. So you could in principle make this from nickel alloy, but it would not only be much more expensive, but it would be more dense. So working with Rolls-Royce, we have created a completely new kind of a shaft material which has a lower density than nickel. It's based on iron, and it contains very fine precipitates of two different intermetallic compounds which give it the perfect combination of properties both for the high temperature end and the low temperature end of the shaft, eliminating the need for any friction welding. And the alloy also has the plasticity that you need in order to temporarily accommodate the problems that arise when you have a fan blade off event. The alloy now has been granted 3 patents, and it has been produced on a large scale. Here you see Paul Hill from Rolls-Royce sitting in front of 3 blanks of the new shaft alloy. And of course it has to have machinability, and it does have that machinability because there are some intricate features that would be machined onto the shaft. So this is another example where density of steel actually beats nickel alloys and is present in a civil engine which actually flies. So the case that I'm making is that density is not a really bad characteristic of steel. Here is another beautiful example. So these are damaged coral reefs near Indonesia, damaged either by mining of coral or by blast fishing. And vast areas have been destroyed in the past. Of course, it is not legal anymore to use blast fishing in these regions, but the coral reef has been damaged really badly. So what do? Well, you make these steel frames out of the cheapest possible steel, ordinary reinforcing bar bent into shape, and you attach live coral to parts of that frame structure, and then you just place it on the seabed. And the density of the steel means that it's not washed away by storms, etc. And look at the next picture, which is really quite remarkable. You can see that the coral reef is completely recovered, and if you look carefully you might see remnants of the steel frame, but here's another picture which shows the steel frame more clearly. So my conclusion is that in engineering design, just to talk about something which is dense and therefore cannot actually be made into rockets or into aircraft engines is just wrong. Now the other bad characteristic of steel that I mentioned earlier is rust. And you can see here a corroded object. And the reason why rust doesn't protect the steel is because the reaction that creates rust actually happens in the fluid ahead of the steel surface, where the iron enters into solution and then the iron ions combine with the water to form the iron hydroxide, which oxidizes further to rust. So that rust is forming away from the surface of the steel, and therefore it does not protect the steel, and corrosion continues indefinitely. And you might imagine from this picture that rust is an ugly thing. We don't like it. And the reason why we don't like it is because in the past, cars were so badly designed that they would rust very quickly. Nowadays, you would not buy a car which would rust in 15 years. The car producer would go out of business. But the color of rust is actually quite beautiful. And this, in fact, is like chocolate color. So this nut, bolt and washer actually is made of chocolate, which I was happy to consume myself. So the color of rust is actually quite beautiful. It depends, of course, on your subjective view, but I like this color, it's chocolate. And there are many other people who like the color of rust. So for example, on the left you see a painting made using rust, and this was at the University of one of the students from the University of Sheffield, who created many of these which were on display. And two ladies from the Netherlands wrote a beautiful, very thick book going around the world taking photographs of rust. And in this book you see beautiful images of rust, and the color, you get to like the color. Now, when I was in Colorado, my colleague David Matlock took me to the Rocky Mountain National Park. And the amazing thing there, which I noticed much more than the scenery, is that all the fencing was made out of the so-called weathering steel. So weathering steel produces rust, which is compact, and therefore it protects the steel. It doesn't just flake off. So all the fencing in this national park is made from weathering steel, and even the buildings that you see are made of weathering steel. And the huge advantage is there is absolutely no maintenance required for at least 40 years. No painting or galvanizing, etc. And furthermore, the color matches the color of the woodland that it serves. So there's a huge advantage in using weathering steel properly. You don't have to galvanize it, you don't have to paint it, no maintenance required. It doesn't produce stains of rust anywhere. From this we should learn that many of the objects that we actually make do not require galvanizing, even though we use it, nor do they require painting, even though we make lame efforts to paint them. So here are just a few of the examples that I photographed myself. So on the left you see motorway crash barriers. Now the mechanical properties of the crash barriers are easily replicated in weathering steel, and the galvanizing is absolutely not necessary because the steel would acquire the beautiful patina of weathering steel, and it would fit nicely into the background. The middle picture is a footbridge in Cambridge, and you can see that efforts to paint it have really not worked out well. Presumably we can't afford to maintain it, and you've got patches of rust and patches of paint and even graffiti, because a painted surface actually attracts graffiti. And you can also see that in the pole in the Cambridge railway station, and that is actually where the rails are located. So it's a dangerous place where people decide to do graffiti. And it's a galvanized pole. It doesn't need to be galvanized. When I was in Japan, I saw lampposts which were completely unpainted and ungalvanized on the road. Okay? And the weathering steel, because of its beautiful patina, is actually used in some of the most historically important parts of London. So here I photographed the pedestrian bridge that is right next to the old Wall of London, which was built 1800 years ago. And this particular bridge was pointed out to me by the master of the worshipful company of armorers and braziers, who said to me, look, you're obviously interested in weathering steel, but do you know that we have this beautiful pedestrian bridge just 5 minutes from the location of this company? And it's really interesting that the original iron bridge was this color. This is after it has been restored to the original color. This to me is a rust color, okay, but it is in fact paint. And the painting process is expensive for bridges. You don't need actually paint. You could just use weathering steel. Of course, this is an ancient bridge built a long time ago, the first bridge ever made from iron, cast iron. In Cambridge, many of the buildings, the new buildings on the biomedical campus, are made from weathering steel. So here are 3 examples. The one on the right is particularly interesting. It's an academy for young, probably something like 10 to 14-year-old students, a science and engineering academy. And you can see that they've even decorated the weathering steel with its beautiful chocolate color. So rust is not always a disadvantage, right? And where it is a disadvantage, we are able to protect it very effectively these days, and we know how to do that. So I've basically ruled out all the bad characteristics of steel other than the pollution. So by increasing the life of steel components, we can actually reduce the amount of steel that we use. Now, one of the things that we teach undergraduates is that martensite, when you produce it in steel, if you have a large carbon concentration, then it will be brittle, and therefore you must temper the steel. Here, for example, is an object created using additive manufacturing, robotically controlled welding system, rather than laser powder and so forth. So that's called metal arc additive manufacturing. And it's a node for beams coming from different directions. Normally, it would be a clunky looking object made by cutting bits of steel and so forth. In this, you save 30% steel because you only need to add the thickness where it's required. Okay? And it looks really rather nice. Okay? And this is an artistic object made using out of steel using additive manufacturing. There are many more examples like this in my book. I'm not advertising the book, but it was written just last year, so there are many, many examples. There's a whole chapter on additive manufacturing of steel. So we can use better technology. I'm going to now give you another example of changing the way in which we think. Now, I had an introduction, so I'm going to go a little bit beyond 7 o'clock. Okay? Otherwise, you get quench cracking. Okay, the martensite plates will be so brittle that they crack spontaneously, and this is an example. So what I wanted to do was to create a high carbon martensitic steel which does not need tempering, because tempering does reduce the strength. Okay, so I want to use it in the untempered condition and yet have impressive properties of the type that I've listed here. So this is like a dream scenario, that we do no heat treatment after producing the martensite, and yet, you know, we have a large amount of ductility, toughness at minus 40 degrees centigrade, and so on. So this is not a dream. In fact, we have done this, and even written it up in my book. So the reason why we can avoid the cracking of martensite plates which are not going to be tempered, is that if you make the distance between cracks so small that the transfer of stress onto individual martensite plates becomes difficult, then the plates will not crack. And that comes from composite theory. So when you have very short fibers in a composite, and that's why, you know, carbon nanotube composites are not successful, you can't actually transfer stress onto the nanotube, because it has too small a surface area in contact with the polymer. So what we want to do is to create an austenite grain size which is finer than the distance between these periodic cracks in martensite plates. So how do we do it? How do we make an incredibly fine austenite grain size of something like half a micrometer? That is a ridiculously small austenite grain size. Well, what we did was we took our 0.35 carbon steel and we rolled it in a proper mill at a very low temperature, something like 800 degrees centigrade. And therefore we produced a severely pancaked austenite grain structure containing lots and lots of deformation bands. So effectively it divides the coherent size of the austenite grains to a very small value. And I can illustrate that slightly differently. Here we have stereographic projections of a single austenite grain, first in the deformed austenite and second in the undeformed austenite. And what you see is that we produce many thousands of orientations of martensite plates in a single austenite grain, which all crystallography would tell you that in the undeformed grain you can only get 24 variants. So by producing a huge confusion of orientations of martensite plates, you deflect any cracks that form tortuously through the structure, and therefore the toughness increases dramatically in the untempered condition. So here, for example, you can see that the new steel has a toughness of 75 megapascals root meters and even a Charpy toughness at minus 40 degrees centigrade, okay, and at a strength level of about 2 gigapascals. And it can be welded as well. So I'll show you one particular application. This is a test to simulate a blast. A blast is a sudden distributed load, and in the university we would test that by firing aluminium foam at high speed onto our steel, which is clamped at both ends, and of course the steel must not fracture, and also it must not bulge too much, because if you're making a vehicle using this for it to be blast resistant, you know, obviously it can't bulge too much into the interior of the compartments where people are. So just imagine, in this very high strain rate test, the material of untempered martensite survives, okay? No problem at all. But we also wanted to look at a civilian application, and this is where the saving of steel that I'm emphasizing comes in. So we decided to look at the properties of this steel during impact abrasion wear. So impact abrasion wear, a simple scenario is where you've got minerals falling onto a steel surface and then sliding. Okay, so you get abrasion due to sliding and impact damage as the minerals fall. And we worked with a university in Tampere University in Finland, who have very good equipment for this purpose. So here, for example, is the movie showing granite particles hitting our steel samples here. This is a slowed down movie, okay? And on the right side, you can see a combination of both abrasion and impact damage. Now, of course, when you do experiments in the university, they may not be representative of what happens in real life. So we installed this steel in a location in Tata Steel where they had significant problems with minerals falling onto a particular steel plate, which was coated with hard-facing alloy. The hard-facing alloy is a very high chromium and carbon alloy containing large M7C3 particles, and you can see it here. It's the hard-facing alloy is deposited by welding. So all that adds to expense, and it wears out into the damage that you see in approximately 3 months. Now, we replaced that with our steel, and this was before the pandemic, and it was examined just after the pandemic, and there is no visible sign of damage. So that's over a period of years, and even now I haven't heard of any damage on this. So by replacing the hard-facing steel with the new steel, we save an enormous amount of CO2. And that is the ultimate goal of developing, that should be the ultimate goal of developing completely new steels, is to reduce CO2 production by using less steel. The most important thing for humanity, because the poorest people in the world will suffer if global warming continues at its pace. Now, I have a really interesting slide, which was from pictures from Ethiopia by my colleague Alan Blackwell, who was on sabbatical in Africa. He works on machine learning, and he was passing some construction sites where, reinforcing bars are used to make buildings, and there's lots of scrap of reinforcing bars. So in the market, he found that people were using the reinforcing bars to make tools. For example, the holder of a hacksaw, which you see, that's made by using scrap reinforcing bar, or a variety of different kinds of tools. So sometimes we treat steel as a cheap commodity where you can waste quite a lot of material. That is not a good thing. Okay, moving on to a current topic. You all must have heard about the collision, almost 90-degree collision between the Solong container ship and the Stena Immaculate, which is a tanker. At the time it was carrying some fuel for jets. And I don't have copyright of the image, which shows a huge gash which developed on the side of the Stena Immaculate when the Solong impinged it. But it was pretty impressive damage. Okay? I should point out that neither of the ship sunk, and only a small amount of fuel was spilled into the sea. Relatively small amount of fuel was spilled into the sea. It's tragic that one person actually from the Solong is missing. But the quality of engineering is something to admire. So here, for example, is a real picture of the Stena Immaculate before it was severely damaged. It is a double-hulled ship. That means there are two hulls. So if the outer hull gets breached in an accident, the oil containing second hull is fine. And of course it's also divided into 18 tanks, which means that if one tank ruptures, then only 1/18 of the fuel will spill out. So a double-hulled ship is schematically shown here, where there is a separation delta X and delta Y between the outer hull and the inner oil-containing hull. Of course, if you make delta X and delta Y too large, then you are reducing the capacity of the tanker, or you're making it wider, which introduces more drag and so on. So one of my former students, Kazutoshi Ichikawa at Nippon Steel, and his team have produced a new ship steel which has so much ductility that you can afford to use just a single hull. Okay? Now, ship owners and ship insurance are not convinced when somebody says something like that until a huge amount of validation is done. And they went through the validation procedure and government specifications and so forth, and insurance specifications. And they have gone through that whole system, and there's a number of ships which have now been constructed using the new steel. Now, I'm going to show you just one of the impressive tests that they do to establish that even with a 90-degree impact, this steel will survive. Okay, this new steel will survive. And of course, you know, there are many other properties than ductility that you have to ensure, like weldability and so on and so forth. You don't focus on just one property. So this particular test is pushing this very large object against the steel plate, and you will see that at some point it will fracture. Here, there's a fracture which would either spill the oil out or let the water into the ship. So the plate is held rigidly, and we are pushing in this huge object into the side of the plate. This is the same test now, but using the new steel. And you will see that with the same amount of penetration into the plate, rigidly held plate, you get no cracking at all. Okay, and there are quantitative data available on this in publications. So this new steel is called N-Safe and is designed so that you can make ships with just a single hull. Now, the curves shown here, the load versus indented displacement, are for the new steel compared with the red old steel, where you can see clearly that the load that it can accommodate and the displacement that it can accommodate is much greater than for the ordinary steel, which has the structure illustrated on the left, and the new steel has the structure illustrated on the right. It's difficult to see at this magnification what the difference is, but it is not just ferrite and pearlite. There is some bainite present there as well. Now, we are in Wales, and it is interesting to talk about bridges across the River Severn. The first iron bridge across the river was, of course, the famous bridge made out of cast iron at a cost of about £6,000 in 1781. And it sounds very little, but in those days the actual quoted price for the bridge was about half that. So it overran the budget. But nevertheless, you know, for the first iron bridge to be constructed anywhere in the world using cast iron was amazing. And of course, you know, cast iron had to be produced, and it was produced nearby in Coalbrookdale. And this is an image captured by an artist of the, if you like, the birth of the Industrial Revolution, with the cast iron being produced in quantity in Coalbrookdale. But you know, what is painful to see is the level of pollution. Okay? Now, this kind of a scenario would not be feasible today. So the problem is that before the construction of large bridges, modern bridges across the Severn, people would have to take a huge detour to get across the River Severn to the location that they wanted. There used to be this ferry which could take a few small cars across the river. And in the background you see the construction of the Severn Bridge, which is a suspension bridge, a long suspension bridge with a long span. And there is also the huge concrete foundation there for the bridge. Now there is a cost associated with the steel and the concrete, and it's quite a large cost, and I've been communicating with David Collins, who works on this, and he explained to me that actually, having a long span of this kind is more expensive in the CO2 cost, both in the concrete and the steel, embedded in the concrete and in the steel, than having a short span with lots of supports. So in places where you do not need a long span, it's perfectly okay to make a bridge which has many different supports. So for example, this is the Prince of Wales Bridge, and you can see lots and lots of supports underneath, and it's a cable stay bridge, and this has a lower CO2 cost than the original bridge across original Severn Bridge. So these days people are doing analysis of whatever engineering construction that they think about, not in just the terms of performance, but also in terms of the burden of pollution. Unfortunately, this is not the case everywhere in the world, but certainly modern engineering considers this as a part of the design scenario. Now, all of this work, making optimum use of steel, creating new steels for better, for a reduction in the quantity that is necessary and so on, it takes time, and we are probably not moving fast enough to avoid disasters which will influence the poorest people in the world, the CO2 induced warming of the globe. So I have a way of cutting steel production by 25% without reducing the quality of life and without causing pain to industry. It sounds like magic, but it is as follows. Okay, it's very, very simple, and I've written about it, I've talked about it, I've even communicated it to the UK government. So the way to do this is very simple, and the reduction can be achieved in a period of just 4 years. So what we need is legislation, because no matter how goodwill you are, you will not actually use best processes. And the clear example of this is in automobiles. Nobody bothered to make fuel-efficient automobiles until the US government legislated that all cars must have a certain level of fuel efficiency. And then everybody followed. So we need legislation which will ensure that there is a tax put on anything that's made out of steel according to the steel component of that object, and that tax would go to industry to support it, to create better processes and better technologies, and that industry can be the steel industry, it can be the construction industry, etc., etc. So in principle, the tax that you collect must apply to both imports and things produced locally, but the tax income should in some way be dissipated to local industry. And in that way you don't cause pain. Tariffs of the type that the US is implementing, and I've said this in the US before President Trump was elected. I said in my lecture, which is on YouTube, that tariffs are no good. They basically inspire inefficiencies in local industry because the competition is reduced. That used to be the fundamental principle of the US, that competition produces efficiency. So instead of tariffs, if you put a tax on the steel content of anything, you will create a scenario in which the best steels are used and the whole life cost is considered instead of just the cost of the steel itself. Okay, I've reached almost the end of my lecture. So I'm going to finish here first by thanking the Institute and the people who considered me as a candidate for this lecture. So I would like to thank Philip in particular, who helped with a lot of the organization, and also of course Stephen, from whom I received the invitation letter, which made me feel very, very happy. Now, a lot of the things that I've talked about today you will find on my website here, free to download, no need for registration, etc. And most of the books that I illustrate are also free to download. The one that you see, the latest book, Perlite in Steels, has a picture of a bridge. That's the longest single-span bridge in the world. It's 2 kilometers unsupported underneath. And I've been there, and it's between Awase Island and Kobe in Japan. All the technology that I've talked about today is written up already. So thank you very, very much for being such a wonderful audience, and that's it.